Okay, we'll get started. I'm delighted and proud to introduce Toby Li's thesis proposal. His committee is me as chair, Tom Mitchell, Jeff Bigham, John Zimmerman, and Philip Kuo from the University of California, San Diego. Tom and Philip are on Skype. And we'll run this the way HCII usually does, or every faculty member gets to pick their own way. So I've asked Toby to speak for about 50 minutes to an hour. Then we'll have questions from the committee, starting with Philip. You get to go first, and then Tom second, and then John and Jeff, and then me. And then hopefully people in the audience will stick around and ask some hard questions. And then we'll go around again until we run out of questions. And then the committee will meet and decide what to do next. So I'll let Toby start.
So, hello everyone. Thank you for coming. I'm Toby Li. Today I'm happy to talk about my proposed thesis work on a multi-modal intelligent agent that nurtured from demonstrations and natural language instructions. Recently, conversational agents have become increasingly popular. Users can have agents perform all kinds of computing tasks on their behalf through conversational interfaces. But first, before we get into conversational agents, let's first look at the role of traditional graphic interfaces, or GUI. It's basically a medium between back-end services and the user. The user manipulates the GUI, and the GUI can often do something by sending API calls to the back-end services, maybe get some results, and then display them back to the user. And as we can see in this diagram, most current agents, like Siri, Google Assistant, or Alexa, they replace the role of traditional GUI, where in situations where operating GUIs is not convenient for users, like when the user is away from the phone, or when the user is occupied by other activities, such as driving, or when the task procedure is repetitive. The agents receive speech commands or automation rules from users. They send out API calls directly to the backend services and return the results back to the user through either displayed or spoken feedback. A key issue with current agents is that they support limited task domains, and users don't know what's supported. If the task you give is out of domain, or if you mention an unknown concept, they will often just give those very generic error responses, which are not very helpful. Here are the two sources of this problem. First, not all services have their APIs connected to the agent. So if the service you want to invoke wasn't connected, the agent wouldn't know what to do. Second, the agent's language understanding capability is also pre-programmed and limited to specific task domains. If you mention a concept that the agent doesn't know about, it will not understand the command. The current approach to expand the supported task and task domains relies on app developers. Companies such as Apple, Google, and Amazon, they all have development kits that allow developers of third-party apps to integrate their apps into the intelligent agents. The developers have to provide two things. First, they have to provide access to the internal APIs to their services and specify the possible parameters, parameter values, and any domain knowledge. Second, they also need to either provide a dialogue model or a large corpus of users talking about the task domain that can be used to train a dialogue model. This allows the agent to understand the user's natural language commands when the user talks about this new task. This process requires a lot of technical expertise and engineering efforts from the professional developers. As a result, only a small set of the most popular apps have been integrated into those agents. Prior work, as well as our formative study, found that there's this huge long tail of app usage and mobile tasks. This long tail of apps have a smaller number of users and are less likely to get integrated into agents, due to the expertise and the engineering efforts required. However, when added up, those long-tail mobile app and tasks, they actually made up a significant chunk of user usage. A solution to this problem is end-user development. We can have end users program the agent what it doesn't know or can't understand. Prior approaches have used techniques such as block programming and end-user scripting. However, the use of such tools are limited to expert power users because there are still significant learning barriers in those tools for users without significant programming expertise. Recently, there has been this new wave of actually easier-to-use end-user development tools like Apple shortcuts or IFTAT, short for if this, then that. With those tools, users can specify simple trigger action automation rules using some pre-made modules. Those tools have got pretty popular because they are very easy to use, but the expressiveness of those tools is limited by the rather fixed structure. The set of task domains they support is also limited because users can only use those pre-made building blocks. So, as I discussed, there are two major barriers preventing end-user programming for agents within the pyramid model. Users don't necessarily have access to the APIs for backend services in the task domain they want to program for. Even if they do, they lack the technical expertise required to program with existing available tools. To address this issue, we adopt a new model here, where the agent actually sits in between the user and the GUI. The GUI here plays a new role as a medium for users to communicate with the agent, and the building blocks with which the user programs the agent. Users teach the agent through coordinated demonstration on the GUI and verbal instruction about contents on the GUI. The agent is able to understand some semantics of the GUI. At program time, the agent can then observe the user's demonstration, while at the execution time, the agent can directly manipulate the GUI. Another important aspect here is that we combine two techniques with different input modalities: verbal instructions in natural language and demonstration directly on app GUIs. Let me go through some background of those two. Programming by demonstration is a technique where users demonstrate the desired behavior directly. It's not a new concept. There have been works on web macros, for example, where the user demonstrates interacting with a web page, and then agents can record them and later replay them. Similar techniques are also used in softwares like Adobe Photoshop and Microsoft Excel. It has a lot of advantages. It's a natural way for users to teach a task. We do that all the time when teaching tasks to other humans. It's also easy. If you know how to do it yourself, you know how to program an agent to do it for you. From the agent's perspective, it's also easy to ground what the user demonstrated to existing GUI elements because the user demonstrated directly on them. However, there are also some drawbacks. Demonstrations only show what the user do, but not why they do it. So it's really hard to infer the user's intentions behind those demonstrations. Therefore, when the agent is in a new scenario, the agent might not know what to do. Because it's very challenging to generalize from those demonstrations. We also use a technique called natural language programming. It's a technique where users describe the desired behaviors in natural language. Early work in this area tries to directly translate user commands into programming language like Java. This didn't really work because this technique requires users to use commands that are structurally similar to programming language, which is really hard for end users. Recent works took a conversational mixed initiative approach. The agent can work together with the user through multiple turns of conversations. Those are much easier to use. However, a limitation is that in order for the agent to engage in this conversation, the agent needs to have prior knowledge about the task domain. Because of this reason, existing agents are limited to a few specific task domains, such as email processing or calendar management. Natural language programming is also a natural way of task instruction, but it has some of the opposite pros and cons compared with program by demonstration. Natural language commands often reflect user intentions and provide contextual information of the task. However, it's often difficult for the agent to ground user commands onto the agent's known concepts, procedures, and entities. Users also don't know what the agent already knows, so they don't know what they can say that the agent can understand. Natural language is also ambiguous. So that's why we're going for a multi-modal approach that combines the two input modalities. There's this important concept of mutual disambiguation. Use input from one modality to disambiguate input from another modality. Prior systems like Plow use this strategy. For example, when a user says, put the name here, and demonstrating filling a text form. The demonstration allows the agent to know what the word here refers to. And the natural language instruction allows the agent to know that this field represents a name. Multi-modal interface is also natural to use. The user can choose between talking or direct manipulation for different parts of the operation, depending on which one is more convenient. We have designed and implemented a system named Sugilite. It's named after a purple gemstone that looks like that. And it's short for smartphone users generating intelligent, likable interfaces through examples. Sugilite is an end-user programmable task agent for task automation. The system is also open sourced on GitHub. Here we identify 6 key challenges for Sugilite. Throughout this talk, I will discuss more about how we address those challenges. The first 2 challenges are actually constraints. While we're making this system more and more powerful, more generalizable, and more expressive, we want to keep the learning barrier low, so users without programming knowledge can use the system. We also want the system to be able to handle long-tail tasks across different domains, which means the system should not rely on any prior knowledge on specific task domains. The rest 4 dimensions are what we want to use to measure the system. How much can it generalize from demonstrations? How much expressiveness can the system support in terms of specifying flexible task logics? How robust the system is, and how much can the knowledge it learns be shared among different users? One thing I want to emphasize is that all my preliminary work and proposed work in this thesis focused on one single system. We started with an original base version of it, and then we iteratively added new components to it to expand its capabilities on those 4 dimensions. A little bit of preview. At the end, it's going to look like this. But let me first introduce the original base version of Sugilite. This work was published at CHIII 2017, and it won a best paper honorable mention award there. We implement the system on the Android platform. Let me first show a quick demo video of the most basic example use case, so you can have an idea of how it's like to use Sugilite.
Order a cappuccino.
Sorry, but I don't understand. Would you like to teach me? Say yes or just ignore.
Yes.
Great. When you say, for example, order a cappuccino, what shall I do first? Say demonstrate to demonstrate.
Demonstrate.
Show me how to order a cappuccino. Once you are done, click on the duck and select end recording.
So you can see the agent asks the user to demonstrate a task that the agent can understand. And the user can just demonstrate it with Starbucks app. And you can see the agent is recording every step the user is doing and showing a confirmation window, which is showing that the operation has been recorded. this step, the agent is actually confused about the action and asking the user to manually specify a data description query, which I will cover later.
Order a cappuccino.
Executing.
And then you can see the agent already knows how to do this, so you can just manipulate the GUI of Starbucks app to perform this task. Let me explain a little bit of how that worked. Sugilite just record all actions that the user demonstrates. This is done by having an Android accessibility service running in the background. This accessibility service will capture data on all the user's actions and data about all the other UI elements available on the screen. For example, in the Starbucks app, when the user clicks on this menu button, the service gets an accessibility event that contains all the metadata about this icon, like this button, but also all the other UI elements available on the screen. The base version of Sugilite just uses a rule-based heuristic to pick a subset of features to identify this button, and generates an operation like this for replaying the operation later. If the heuristic is confused about which features to choose, it will show a dialog to allow users to manually choose, as you saw in the video. But we have another follow-up project specifically focused on this part, which I will talk about later. An emphasis of my work is generalization. In this version of Sugilite, it generalizes the script by identifying parameters and their possible values using a combination of the user's natural language command, the demonstrated actions, and the structures of app screens. For example, suppose a user is demonstrating for a task, order a spicy Italian pizza. When the user reaches this menu in the Papa John's app, we can see that the user will click on this option that has a text label, spicy Italian. Look at this menu structure. Sugilite can tell that, okay, spicy Italian is likely a parameter in this task, and here are all those other possible values that can go into this parameter. This way, we can allow users to later say things like order a barbecue chicken bacon pizza or order John's favorite pizza without having to demonstrate again, because the system can recognize the parameters and the values. Sugilite also has error handling features to ensure the robustness of a system when executing a script. It will first check if the current screen matches what was demonstrated. If the app ended up in an unexpected state, Sugilite allows users to create error handlers. For example, if the user demonstrates how to request a Uber under normal pricing, but then run a script when there's surge pricing going on, Sugilite will get stuck because it doesn't know how to handle this pop-up because it has never seen this before. In this case, it will just ask the user what to do in this case, and the user can demonstrate how to handle this pop-up. This mechanism also handles permanent changes to the app GUI. For example, if an app has changed its GUI structure permanently, the user can demonstrate what to do in the new version of the GUI and use this replace option to replace the corresponding parts in the old demonstration, as opposed to in this Uber example, the user will use the create fork option, so the agent can handle both the surge pricing and the normal pricing. Sugilite also supports cross-domain tasks. There are many smartphone tasks that involve multiple apps. For example, for planning a dinner, one may need to use apps like Yelp, Google Maps, and Calendar. Sugilite allows the user to teach the agent tasks across multiple apps, and also transfer information between those apps. I will now show you a video demo of some of the features I just talked about. You can see that's a result of parameterization from the script we just created. it recognizes all the other kind of drinks you can order from Starbucks app, so I can choose a different kind of drink. And it will use the same procedure to execute the task to order this different kind of drink. This is an example of the error handling. So here, basically, the pizza the user wants to order is not available. So the user can demonstrate a new type of pizza to order. And you can see in the script, it's basically a try-catch structure where you will first try the first branch, but if it cannot find the option, you will try the error handling branch.
Find the route to the highest rated restaurant nearby.
Run script, find the route to the highest rated restaurant nearby.
And that's an example of a cross-app script. You will first open the graphical app, find the restaurant, and you extract the address and put that address into Google Maps to find the direction to that restaurant.
Check the score of New York Yankees.
Run script, check the score of New York Yankees.
And users can also use Sugilite for information query tasks, such as opening the Yahoo Sports app
Result,
and read out the
Yankees
scores.
SOXL4 final 59/18.
Pay off my credit card balance.
Run script, pay off my credit card balance.
You can see from GUIs can really have access to all kinds of apps, including those that won't normally open up their APIs, such as banking apps.
Tell Julia I will be late because my car is broken.
Run script, tell Julia I will be late because my car is broken.
And you can also have those like really shortcuts with different parameters. We conducted a usability evaluation for Sugilite. In the study, we asked 19 participants with different levels of programming expertise to use Sugilite to program 4 common tasks. In the results, the participants they completed 85% of the tasks. Our result also suggested that users with no programming knowledge can operate Sugilite as well as programmers. So this chart basically shows the time on task, and those 1, 2, 3, 4, they represent the task, and those bars with different colors represent users with different levels of programming expertise, and we saw no significant difference between those. Based on the original Sugilite, our first extension is named Applesit. It extends the use of Sugilite to smart home automation and adds support for many different ways of triggering Sugilite scripts, which allows a higher level of expressiveness. This work was published at ISEUD 2017, and it won the Best Paper Award there. Many companies have established the model of ecosystem for their smart home offerings. In such systems, the user often has a hub that mediates all the communication between devices. And the hub also controls the devices in the system. The user can then connect compatible smart home devices to the hub. For both commercial and technical reasons, the users are often limited to use only devices from the same manufacturers or manufacturers that have collaborations. Like in this case, basically a bunch of LG devices are connected to an LG smart home hub. So this is a closed ecosystem. However, this closed ecosystem model is not ideal in many aspects. There are many different kinds of components that can be involved in a smart home, and none of the ecosystem can cover all of them. Many users also have already acquired some devices, and don't want to be limited by only being able to purchase devices from the same ecosystem when expanding their smart home system. What the user wants are end-user development systems with compatibility and interoperability. They want systems that can be used for programming for all the devices they have and can enable data transfers between those devices. We found that almost all smart home devices, from light bulbs to cars, they have corresponding smartphone apps thanks to the ubiquity of smartphones. Those apps usually serve two purposes. First, it displays the status, the reading, or other data from the device. Second, it also allows the user to control the device using the app. The design of those apps often follow common app design patterns, so they are pretty usable for end users. In most cases, end users should be able to use those apps with little effort or outside help. So in our approach, to leverage those resources, we designed a mechanism that can use smartphone as a hub for smart home automation, enabling users to program smart home automation using the existing apps through Sugilite. Let me show an example of how Sugilite can be used to control smart home devices. You can see in this case, we have a script that can invoke the Flip Hue app. And the user can specify the color. And Sugilite will just invoke the Flip Hue app to turn on this light and make it green. The user can also extract data from off-smartphone sensors from app interfaces. For example, here, the user can extract the last detection time from this motion sensor through the app. Sugilite provides useful additional ways for triggering scripts besides using a Sugilite app and by voice command too. So a Sugilite script can be triggered by app launches, by phone notifications, by smart home hubs such as Amazon Echo, or by smart home sensors or external services such as email or Twitter through the integration with the platform IFTTT. Then the next follow-up work we did was a component called AppNight. It's a new interface for inferring the user's intention for demonstrated actions to support the development of more expressive and more generalizable scripts. This work was published at VLICC 2018. In programming by demonstration, a central challenge is called the data description problem. It's about the question, when the user demonstrates an action, what does it mean? When the user demonstrates an action, there are many possible features that can be used to describe the action and the target item. In order to represent this action in a way that can be replayed correctly in different contexts, the system needs to determine a subset of features that can reflect the user intent. For example, if you look at this action, where the user selects a restaurant from a list of open table search results, there are many different reasonable ways we can interpret this action. The easiest thing to do is to simply record this as clicking on this exact pixel location. But that won't be very useful in a different situation where I have a different list. You can also record this as click on Charles Palmer Steak. That doesn't really work well for different search results either. What we really want is to be able to read the user's mind to know why the user selected this one. So we can understand the user's intention on why they choose this one, so we can automate the task in a way that reflects the user's intention. There are some prior approaches to this problem. Each has its own limitations. The first approach basically makes no inference and asks the users to manually specify their data description. It gives the user full control, but it's very tedious and also hard for non-programmers. There are many prior studies that show that non-programmers are not really good at doing this. Another hybrid approach is to use heuristic rules in conjunction with manual specification. So in simple scenarios, a heuristic rule will just generate data description. But when the situation is more confusing, it will go back to the user and ask the user to specify the data description. That's what we used in the original Sugilite system. So for simple actions, such as clicking on an icon, the data description is automatically inferred. But for more complex actions, such as here, the user basically selects an item that says cappuccino 120 calories. The system doesn't really know if the user's intention is to order a cappuccino or to order something that has 120 calories. So it basically shows a dialogue that asks the user to manually choose one. In our study for original Sugilite system, users were actually really confused when it comes to this dialogue, so it's not really working well. A third approach is to use program synthesis methods on multiple examples. However, this approach requires multiple examples that show what to do in different situations to cover its whole space of different branches. For complicated tasks, the number of examples required can be really substantial. Prior studies have also shown that non-programmers are not really good at providing meaningfully different examples. So if you ask them to provide an additional example, they may very likely provide you something that's essentially the same to the original one. We came up with a new multi-modal approach to this problem. We introduced a new interface named Appnite to enable users to provide natural language instructions to express their intentions for demonstrated actions in the context of third-party mobile apps. It can infer data descriptions for demonstrated actions from natural language instructions. It's an acronym that stands for Automation Programming on Phone Interfaces using natural language instructions with task examples, and it's named after a rock that looks like that. We conducted a formative study to evaluate if users are able to explain their ambiguous actions in GUIs. I'm going to skip the study design details. You can refer to the proposal document if interested. But the two main insights are, first, when we ask the users to verbally explain what they're doing, what they say are actually useful for inferring data descriptions for demonstrated actions. Second, in their explanations, they refer to many different kinds of features that are visible on the screen, such as text labels, spatial layouts, and also hierarchical structures of GUI elements. Based on what we learned from a formative study, we designed and implemented Appnite based on the original Sugilite system. Let me walk through an example of how it works. Suppose a user demonstrates clicking on an item in a search result in OpenTable. The first thing it does is that it will try to determine whether its action is ambiguous. If not, it will just simply use heuristics to generate a data description, which is the same as the original Sugilite system. But if the action is indeed ambiguous, it will ask the user to explain her intention for this action in natural language. Like for example here, the user can say things like, I want to find a steakhouse in Midtown East. In order to parse this natural language instruction and ground it back to the GUI of OpenTable app, Appnite represents the screen in a UI snapshot graph. And then it will really parse this natural language instruction as a graph query over this graph. For the next step, it basically parses this into this formal representation. And then you will execute this query on the original graph. So like for example, in this case, it basically queries for any element on the screen that has text steakhouse and also has the text Midtown East. Then it checks whether this statement can uniquely identify a target UI element. If so, it will just go ahead and store that as a query to use. Otherwise, it will require further disambiguation from users. So the system will engage in multiple turns of conversation to ask for clarification. You can see here, it basically says, oh, your query matches 2 items on the screen. How should I differentiate between those 2? So the user can say things like, choose the closest one. And that also gets parsed. At this step, in order to help the user provide more useful instructions, we actually display an interactive visualization overlay on top of the original app. So like in this case, the red indicates that that's the item the user originally demonstrated on. And the yellow highlights basically the false positive. It's the item that the user's original description will also match. So here we basically just ask the user, how is the red one different from the yellow one, and how should I choose from them? This mechanism helps the user to focus on what's useful for disambiguations in their explanations. Again, the user's new explanation is now sent back to AppNight and get parsed into a graph query. So you can see here, when the user says choose the closest one, basically it gets parsed into a filter that says, okay, choose the one with the smallest distance value. And it goes back to the loop, gets executed, and check if it's still ambiguous. This process will go on until AppNight has an unambiguous data description. AppNight also has error handling mechanisms built into this loop. So if the user has been through the loop more than twice without making progress, it will provide more detailed instructions to help the user to give more useful inputs. Let me show a quick demo video that shows the process I just talked about.
Please describe your intention for this action.
I want to view all the Italian restaurants.
Is this description correct?
Yes.
Do you want to record the operation? Click on the item that has text Italian.
Yeah.
Please describe your intention for this action.
I want to find somewhere in downtown.
Is this description correct?
Yes.
This description matches 3 items on the screen. Please provide an additional instruction for finding the correct item.
Select the closest one.
Is this description correct?
Yeah.
Do you want to record the operation? Click on the item that has text downtown with the shortest distance.
Yes.
So AppNight represents app GUI screens as what we call UI snapshot graphs, and use a semantic parser that can parse the user's natural language instructions into graph queries on such graphs. I'm going to skip the technical details for the sake of time, but you can refer to my proposal document for all the details. One thing I want to mention is that this graph also encodes the spatial layout of the screen. In our formative study, we found that spatial relations, such as the alignment and layout of UI elements, really suggest semantic relationships. For example, when we ask the user to provide data description for this string, 112, user might say, that's a score for Minnesota. But in this graph representation, that should translate to, okay, that's the numeric value that's next to the string Minnesota. To evaluate whether users are able to use AppNight to specify data descriptions for ambiguous demonstrated actions, we did a lab usability study with 6 participants. In this study, each participant used AppNight to specify data descriptions in 20 sample scenarios in 8 popular Android apps. They also filled out a usability survey afterwards. Let me summarize the key results from the study. Our participants succeeded in producing the intended data description on the first try in 87% of scenario instances. All the rest were also successfully completed in retries after being prompted by AppNight. This result suggests that AppNight is usable for end users to specify data descriptions in programming by demonstration tasks. In the survey, users also considered AppNight helpful, natural, and easy to use. The third follow-up project I want to talk about is called Comments. It further extends Sugilite on expressiveness and generalizability by allowing it to learn task-relevant concepts from the conversations. It was published at WIS this year. Let's look at the example here. If the user says, if the weather's hot, order a cup of iced cappuccino, the agent may either not know the concept hot or the procedure of ordering a cup of cappuccino. The original Sugilite system focused on learning the procedures, but in Comments, the focus is on learning concepts, like what does hot mean? A prior approach to this problem is to have the user verbally explain the concept. But the caveat is that it requires the agent to already know some other concepts that the user might use to explain the first one. If the agent doesn't have sufficient knowledge about the task domain, the user often either can't provide additional useful information because the user doesn't know what the agent already knows, or the user may introduce even more unknown concepts when trying to explain the previous one. Like in this case, the user say, oh, when it's hot, that means I'm sweating, but likely that's not something the agent knows about. So this is also a problem of the users don't know what they can talk about that we mentioned earlier. To help us design a new approach, we conducted a formative study. We asked mechanical Turk workers to describe task automation rules to an intelligent agent. To avoid bias in their language, we showed prompts in graphics instead of text. This is known as the natural programming elicitation method. We divided the workers into 2 groups. The experiment group were shown the screenshots of relevant mobile apps, such as, for example, Starbucks and weather apps. And the control group didn't see any screenshots. They only saw the prompts. Our hypothesis is that app screenshots can help users with describing the task. Here are some of our key findings. Unsurprisingly, users often use vague, unclear, or ambiguous concepts in their instructions. And users often assume the agent to have some common sense knowledge and common sense reasoning skills, like the meaning of good weather, busy day, heavy traffic, or that an easy class can mean the class has a high average score. Between the 2 groups, users who saw app screenshots, they used significantly fewer vague, unclear, or ambiguous concepts. They also tend to use a language and structures directly from the apps they see, which will make natural language understanding much easier from a system's perspective. We think one possible reason of this outcome is that when we show users app screens, users then kind of know what they can talk about. They know that they can talk about things they see on the screen, and they can expect the system to be able to understand them as well. From these findings, we come up with the idea of using app screens to help users instruct concepts in the context of task automation. So we designed and developed the Comments system. It's named after a type of block that looks like that. And it's an acronym for programming a user-friendly multi-modal interface through conversations and examples. We took a multi-modal approach where we had the user start with a high-level natural language instruction and then recursively clarify any ambiguous, unknown, or vague concepts through natural language conversations and references to third-party app GUIs. Let's look at the video demo for example.
If the weather is hot, order a cup of iced coffee.
How do I tell whether the weather is hot?
When the current temperature is above 70 degrees Fahrenheit.
I think what you meant is, the value of a concept current temperature is greater than 70 Fahrenheit. Is this correct?
Yes.
How do I find out the value for current temperature? You can explain or say demonstrate to demonstrate.
I will demonstrate.
Please start demonstrating how to find out the value of current temperature. Click OK to continue.
So here the user can basically
You
go
want to
to
report the operation.
the weather app and refer to basically the reading where the current temperature is.
Do you want to record the operation? Set value of OK, I learned how to find out the value for current temperature. OK, I learned how to tell whether the weather is hot. How do I order a cup of iced coffee? You can explain or say demonstrate to demonstrate.
I'll demonstrate for you.
So the rest is basically going to be the same like as the original Sugilite system, so I'll skip that part. But this figure shows the conversation structure of the interaction we just saw. It's a top-down structure with lazy evaluation. So at the top, the agent recognized the conditional structure, but it didn't understand either the condition or the action. So it uses those resolve functions to represent those. You can see those resolve functions are typed. The first one should expect a Boolean value, and the second one expects a procedure. And then the system will recursively resolve those resolve functions in a depth-first way. Along this process, it basically learns the concepts like it's hot, it learns some Boolean values, it learns value queries, and also procedures of performing tasks. Those are stored in a persistent knowledge base, which I'll explain later in more details. Pumice used type-based highlighting to help users demonstrate value queries. For example, at this step, although it doesn't really understand what compute time is, it knows that it should be something that's comparable to 20 minutes. Therefore, in the demonstration, it basically highlights all the time values on the interface to ensure that whatever the user selects can actually fit into this expression with a compatible data type. A key goal of Pumice is to generalize from what it has learned. And there are different levels. It learns 3 kinds of knowledge and stores them in a knowledge base. There are procedures of doing something, like ordering coffee. For them, it supports parameterizations, so it learns how to order any kinds of coffee from this one demonstration. This has already been discussed in earlier. And the second type is for concepts. In Pumice, concepts are context dependent. For example, the concept hot in if the weather is hot, order iced coffee can have very different meanings from if the oven is hot, turn the oven down. In Pumice, it generalizes this concept hot to a temperature is greater than another temperature, and then associates the actual implementations to the specific task, like ordering coffee. So like here, if I introduce a new task, like if I say, if it's hot, remind me to bring my water bottle, it will ask, in this case, should I find out if it's hot using the weather app, the oven app, or something else? And then ask if there's a new threshold for hot for bringing water bottle. There can also be multiple value query implementations for the same name of the value. Like when we say temperature, there can be multiple ways of finding out the temperature depending on the context, depending on whether we're talking about the weather, the oven, or something else. We conducted an in-lab user study to evaluate the usability of the system. We recruited 10 participants, including both programmers and non-programmers. We gave each participant 4 tasks in random order. In each task, the participant teaches the agent an automation rule with a condition, as well as all the corresponding value queries and actions. To avoid bias in the language used, we also represent a task prompt in graphics. Here are 2 example tasks we use and the possible natural language instructions for them. The study results were encouraging. All participants were able to complete all 4 tasks. They had some minor issues with speech recognition and semantic parsing, but they were able to recover from them on their own. In the post-study survey, participants reported that they found comments easy to use, natural, and also useful. We found no significant difference in time on task between programmers and non-programmers. They on average spend around 5 to 7 minutes for each task. So basically, that indicates that non-programmers can also use comments. So that's a preliminary work I've done for my thesis. For future work, I propose designing 3 new components and extensions for Sugilite to improve it on the dimension of shareability and robustness, including a privacy-preserving script sharing mechanism, a new error handling approach, and an improved natural language understanding module. At the end, I also plan to conduct a field deployment study for this one integrated Sugilite system. The current Sugilite system has limited natural language understanding capability. It uses a grammar-based semantic parser that was trained with a very small corpus. So as a result, it's not really good at understanding diverse expressions. For example, it can understand if I say when the current weather condition is snowy, or if the price is higher than $10. But if I say when it snows, or if I need to pay more than $10, it will not be able to understand those because the limited grammar doesn't really cover those structures. So you can see the ones you can understand basically follows. Okay, something, a property is something. So that's a very fixed structure. Moving forward, we plan to start with collecting a large set of diverse utterances on the user's natural language commands for intelligent agents. So with that data set, we can look at if we want to expand the grammar we use, or if we want to try a different parsing approach, such as a neural net-based parser, in order to handle those more diverse and more flexible commands. Another planned work is to support better error handling. As I discussed, the current version of Sugilite has an error handling mechanism for handling execution time errors when running a script. I plan to expand this error handling mechanism to support handling errors encountered in the dialogue system's natural language understanding pipeline, such as speech recognition, intent classification, and entity extraction. And this problem is particularly important for end-user programmable agents, because for those end-user developed tasks, the agent has a very small amount of language data available. Sometimes just one data point, one example of how the user talked about the task when demonstrated. As a result, the natural language model for this task is very brittle. If the user uses a slightly different natural language command, there's a good chance that the system will not be able to correctly understand it. So we want to develop a new approach that helps the users to recover from natural language understanding errors. And through this process, they can incrementally make the natural language model stronger and more robust. We're currently exploring using the resources of existing mobile apps, so having users refer back to the app content. And we can leverage the semantic information that we can extract from app GUIs to help us to build a better natural language understanding model. The third aspect of future work is to support privacy-preserving script sharing. Prior studies have found that privacy concern was a major barrier preventing users from sharing their program by demonstration scripts. Because PBD systems, they learn from observing user interface actions. It may very likely include personal information on the GUIs in the result scripts. For example, here we can see those GUIs. They may contain personal information such as the user's name, the user's reward balance, order history, or address. In this example, we can see that when a user demonstrates a step of choosing a bank account when paying off the credit card debt, Sugilite actually records the credit card, the account information of users as a data description for this script. So you can see here it says, oh, click on this item that has this test, the user's account number. So this will be really problematic if the user wants to share those scripts. So let me briefly explain the proposed method we want to use for identifying and masking private information on the GUI. So let's use the American Express app as an example. For all Sugilite users, we want to collect the hashed content of what they see on each screen in the American Express app in the background. So we have that information from many users. And then when a script author wants to share a script, we can compute how unique each piece of information is in the script. Intuitively, for personal information such as the account number, not everyone who uses the same app, who sees the same screen, will see the same account number on that screen. But for non-personal information, such as the screen next on the next button, everyone should see the same information. So we can consider the more unique information to be potentially personal. And then we can, by default, mask those potential personal information in the shared script. As a last piece of my thesis, I plan to conduct a field deployment study for the integrated Sugilite system that contains all the components I talked about today. We have conducted a few lab usability studies for each individual components of the system, but a real deployment study in the field can help us understanding these important research questions, such as, can they actually use Sugilite? What errors or what barriers they encounter in real life? Do they actually find it useful? What do they actually use it for? And how do they naturally coordinate the two modalities in real life context? And what kind of context do users actually use Sugilite in? We can only find out those answers through a real deployment study. Method-wise, I plan to have a small group of around 20 to 30 users and having them use Sugilite in their everyday life for at least a month. During this process, I will use a mix of qualitative and quantitative methods to investigate the research questions I shown in the previous slide. We're also going to collect scripts that the user creates using the privacy-preserving method I talked about earlier. So if you're interested in participating in the field deployment study, let me know. I'm also happy to hear any interesting use case that you can think of. In terms of timeline, I plan to have a typical 18-month timeline between my proposal and my defense. So I hope to graduate at around spring 2021. To summarize the contributions of this thesis, we built a multi-modal end-user programmable system named Sugilite. We show that this approach is usable for end users on smartphones. We presented a generalization mechanism that can infer task parameters and parameter values by combining the user's natural language instructions, demonstrations, and the hierarchical structure of app GUI. Then we developed an extension that allows users to use Sugilite to create smart home automation for devices from different ecosystems, and added different ways of triggering Sugilite scripts using IoT sensors, app launches, and external web services. Following that, we designed and implemented a multi-modal mixed initiative interface to help users disambiguate their demonstrations to address this long-standing data description problem in program by demonstration. To achieve this, we developed a technique for grounding natural language commands to F3 entities through the construction of UI snapshot graphs. Lastly, we designed a top-down conversational framework that can learn concepts in task conditionals and generalize those concepts through a mix of natural language conversations and demonstrations. For the remaining part of my thesis, I propose to develop a new privacy preserving script sharing mechanism, a new error handling approach, and an improved natural language understanding module. At the end, I will conduct a field deployment study to understand the usage of this one integrated system in real-life context. That concludes my proposal. I would like to thank my awesome committee, Brad, Jeff, John, Tom, and Philip, for their support, guidance, and mentorship. Without them, none of my work is possible. These are also my loved family. My wife, Julia, who's over there. My 3-month-old daughter, Talia. She's outside, okay, she's outside. And my cat, Doc, I assume he's not here. They are just fantastic. Then the list of my awesome research collaborators and HCII friends. It's a long list, so I apologize if I miss anyone. But you have been all really great and great friends, great colleagues, and I've learned so much from all of you. I mean, we've been through all the highs and lows together, and you folks are certainly highlights of my journey in the past 4.5 years. Lastly, I really appreciate my study participants, mechanical Turk workers who have worked for me very briefly. And reviewer number 2, who made snarky comments. I don't know who that is, but I don't really want to find out either. And that's it. I'm happy to take questions.
Philip, do you want to go first?
Yeah, so great talk. Can you all hear me okay?
Yes.
Okay, great. Well, this was an awesome talk. I also had a chance to look over your the written proposal, and it's very clearly written and everything. I guess I'll start with a really specific question that I think gets to a higher level idea. So can you go back to slide 65? It's also good to have slide numbers. So go to slide 65 on the Appenite. And while you're going to that, I'm just curious about the choice of using, I guess, NLP and speech for doing the disambiguation here. Yeah, so the right side of the screen, right? So it's like there's ambiguity, and then you say, or you can imagine typing a natural language thing, and then you also can demonstrate. So what do you think the advantage of the natural language is there versus, can you imagine making a menu-based approach like you had in the original system? Like, I'm just thinking, is this something, it's cool technology, obviously, to go through natural language, but is this a sufficiently complex domain that the natural language would have advantages, or do you think just the, more traditional tree-based menu could work in this case? And the more general version of my question is, where do you think the natural language has the most power in this whole system versus, just making people select things?
Right. That's a great question, and that's really one of the core problems we're trying to solve in this thesis, is how can we combine those two modalities. I think one advantage of natural language is that it's really flexible. The user can say multiple criteria at once, and it's fairly natural to do that. Because if you look at this example, if you want the user to compose this query, either through manually typing that out or selecting this through a tree-based menu, it's probably pretty complicated. And this can even get more complicated, like the example I showed about sports scores. Because for that one, a part is that the spatial relationship, that the score is next to the team name. That's actually implicit. if you ask an end user to do that, the end user will probably not be able to specify, okay, I want to choose the numeric string that's aligned with the team name. But for natural language, the user may just say, okay, that's a score for the team. And then we're able to basically develop this intermediate level of representation that can translate that into something we can query on in this representation of app GUI. So like when users say, oh, that's a score for this sports team, we can actually translate that to, okay, that's a score that's spatially aligned with this team name. So I think that's one advantage of natural language.
Great. Well, thank you. I can ask more later, so we'll move on to the next committee member. Thanks.
Okay, Tom, you want to go next?
Sure. Let's see. Toby, that was a very good presentation. As you know, I like work. I guess I have two questions I'd like to ask first. It seems that there's a kind of trade-off here. In dealing with the problem that you were calling data description, or which in other words you might call the problem of generalizing correctly from the specific demonstration the user has shown us. And it seems like the trade-off is something like, or one of the trade-offs is who gets to take the initiative in this conversation and when. So for example, if the user gets to have the initiative, then they can tell you pretty directly what they intended to do, but now you have a kind of difficult open-ended natural language understanding problem. Whereas if the system gets to have the initiative, then it can phrase questions just like those airline reservation systems when you call them on the phone do. They can phrase, because they run the conversation, they have the initiative, they can phrase questions in a way that they're pretty sure they're going to be able to understand the answers. So I wonder, I wonder two things here. One, do you agree that's one of the kind of fundamental design trade-offs? And then if so, what do you think about how to manage that?
Yeah, I agree that's one of the really central problem. So I think like in my past work, I've been tackling this problem from, I'll say, two directions. One is enabling user to take initiative, but constrain what they can talk about, either explicitly or implicitly. Like the finding from the finding, we can see that when we show the user a screen, the user will naturally talk about what's on the screen. That will make the natural language understanding problem much easier. But another direction we tackle this problem is to have the agent to take more initiative. Like in the AppNight system, I think the interactive visualization overlay, that's a good example of how we have the agent to initiate basically a prompt that basically specifically asks the user, okay, how are those two or how are those three options different? And how should I differentiate between those three? So I think those are two approaches that we have taken in the past work. But in the proposed future work, I think there's also the error handling problem. Because what we're trying to do is basically we're tackling the problem where the user has already taught the system something, but the natural language understanding part of the system isn't powerful enough to understand when the user refers to what has taught the system in different ways. So our proposed approach is basically similar to the first point I talked about, is to try to refer the user back to the app contents. so that basically we can get user back to a domain that we are more familiar with. So we have more resource, more data, and more basically semantic information to work with. But yeah, I agree, that's like one of the really central problem that I'm trying to solve.
Okay, good. I think that also ties back maybe to Philip's question about text versus speech, and I think to the degree that some of the techniques that you would use to direct the user's attention and to get them to say understandable things might be easier to do in the case of speech interface than text, because you can kind of in real time align what they're seeing with what you're hearing. Anyway, let me ask my second question. In my experience with humans, I found that they're often incomplete when they give instructions. So for example, you had an example where you said, here's an instruction, set me a 7 a.m. alarm whenever the traffic is congested. And you took us through how the system could be taught that. Seemed reasonable. But in fact, if someone instructed the system to do that, they might later realize they don't really want to be woken up at 7 a.m. when the traffic is congested on Sunday morning.
Sure.
And maybe they forgot to say that the first time around. So in some of the tests of just interactions with humans, in some of the work you've done, I know, and some of the work we've done together, we see this kind of overlooking details. I mean, it's kind of the difference between being a programmer and just speaking to another human about what you want to do. So that makes me wonder, how big is the issue here of users needing to refine subsequently the instruction that they gave earlier? And can you, I'm curious what you think about that problem in general, but also I'm curious how the user studies that you have in mind might be able to grapple with that.
Right. Yeah, that's a great question. I think there are, let's take the example you use. I think there are 3 places where you can potentially catch this error. The first one is to catch it right after you specify this rule. But that will require to have either have some like pretty common sense reasoning skill to be able to understand that, oh, most people don't want to be waked up early on weekends. That will solve the problem, but that will require domain-specific knowledge, which is totally another problem that is hard. And or you can just connect usage data from different users. If you see most people have a constraint on not do this on weekends, and you can recommend that, but that would also require to have task domain-specific data. And the second place where you can catch that error is during the execution. Because one characteristic of our approach is that it performs a task by executing on existing user interfaces. So the whole procedure is visible to the user. So if the user is paying attention to the phone while it performs the task, the user can potentially stop it if the user sees it's not going down the desired direction.
Mm-hmm.
But that also has limitations because that requires the user's attention. And the third phase is basically after the error has already happened. So after basically the first time the user was waked up in the morning on weekend days, then the user can basically revise the original rule to add this new constraint: don't do this on weekend. So I mean, I think ideally we want to have a combination of all those three, but I think in near term, the number 2 and number 3 are more feasible, but number 1 is really difficult because it's something that the whole AI community has been working on for quite a while.
Yeah, just quick follow-up. I think the user studies you have in mind are interesting and complicated enough already. But I still want to ask, do you think there's a way to capture or observe or measure this kind of need for delayed refinement in the user studies? Do you see a way to do that?
Sure. I mean, one way we can possibly capture that is by basically doing experience sampling. We can basically send out surveys and basically at different times of the day, and basically ask the user if they can think of anything that anything they encounter that they can use this basically revision strategy to fix a script they originally created. I mean, we can also instrument the Sugilite system that we use for deployment study, so that whenever the user goes back to an existing script and try to change anything, we can ask them basically what happened and why they are doing this as a part of a study to basically just get a sense of this phenomenon.
Okay. I'm good for now. Thanks.
Okay. Next one.
So, great work in addressing a number of well-known problems in user programming. There's been like 25 years of work in this area, and it seems that the biggest problem is that people, not that they can't do it, but they just don't really want to do it.
Sure.
And you're addressing the technical problems, but sort of sidestepping if anybody will do this with this sort of, I'm going to deploy it, and I'm hopeful people will use it. And I'm questioning that strategy, but also proposing, would it be good also in your user studies, you've been giving people tasks to do, which is clear because you have specific aspects that you're trying to address, but it seems like you could collect tasks users claim they desire to do, even like instead of waiting for them to build it. And as a way of dealing with your deployment, could you even give them those? But I think, kind of coming back to Tom's point, a lot of the things that you're demonstrating don't seem super useful. So even in sort of making the case, so that like wake me up if the traffic is bad,
Right.
unless it's a weekend, or if I'm not in town, or if I'm going to work tomorrow. Like the space of ambiguity there is really big, or like order this coffee when it's hot.
Right.
As a demonstration, it's fine, but in reality, nobody actually wants that. So can you ground this in things that people actually would automate? And I'm trying to get a sense, like one question you don't seem to have asked is, how frequently do you do a tedious task on your phone that you would prefer to automate? Is that one of every 20 things I do? Is that one of every 200 things? I'm trying to get, is there a way to get at the usefulness?
That's a great question. So during the user study we have already ran, I always ask our participants, if you had this tool, what would you do with it? And the interesting thing is, most people were able to come up with something that they claim they would do if they had a system. I mean, we don't know if they would actually use that, but at least they said they would use it. But the funny thing is, most of them, they all said the tasks they come up with were all different. So I think that validates our claim of there's this huge long tail of tasks that a small group of people want to do, so that's not big enough, not worthy for a professional developer to do it, but this small group of people will find it really useful. So I'll give some examples. So such as, for example, one participant we talked to, he was an IT administrator, and a large part of his job is to basically monitor the status of some servers they have on Amazon AWS. And one task he proposed was to basically have a Sugilite to monitor the dashboard for him, because AWS has a mobile app, and basically warn him if anything went wrong. So that's one example of basically using this kind of system to automate a professional task.
Does Sugilite have a way of expressing, like, check every 10 minutes, every hour? Because
Not at this moment, but that's fairly straightforward to add.
so are you doing any mapping from the examples people give you? Like, oh, Sugilite couldn't actually do this unless we added these capabilities, so that you know what's going to be deployed is robust to the things people actually want to do.
Sure. Yeah, I have a list of those. And another example, actually one of my personal example is, since I now have a 3-month-old daughter, like a newborn, we change a lot of diapers. So one thing I do is I use the app to track any diaper changes. But that app doesn't really have like a Alexa skill or a Siri skill. So I have to actually go into that app and record a diaper change and say, okay, I changed a wet diaper. But that's something I really want to automate. That's something I really want to bind to a voice command, because that's much easier, right? Because my hands are occupied. I can just say, hey, Alexa, I just changed the wet diaper. So that's also, personally, that's something I would like to have.
So really great talk. I really liked how you framed the work in this long history, as John alluded to, and yet went through like the various limitations and kind of your approach to fixing it. I thought that was actually really good and fairly comprehensive. I kind of left still wondering, so a few times, I think you motivated this by not wanting it to be for programmers, and yet I kind of left the talk still thinking that it's felt like programming.
Okay.
Where there's lots of these status messages. I had to kind of understand what a procedure was. Originally, well, some of the earlier versions, I had to know kind of explicitly what a concept was, and then it kind of let me define it. There was this like recursive thing that like, I was wondering if you could help me understand both kind of, how do I see this as a non-programming task? And then kind of very related, you mentioned that a couple of different studies that the programmers and non-programmers both seem successful. I was wondering how you define non-programmer.
Okay, so yeah, specifically for non-programmers, in my study, I basically define non-programmers as those who have never taken a college level CS course. So basically I have a 5-point scale. So basically 3 is have only taken a college level, 1 or 2 college level CS course, and that's considered programmer. So non-programmer are 1 and 2. 1 is those who have never programmed, and 2 are those who have only used end-user programming tools, such as Excel functions. And going back to your question on programmer versus non-programmer, I think because besides those work, like in 2017, when I interned at Microsoft Research, I actually used some of the similar techniques to build a programmer tool for bootstrapping chatbots, but the techniques are similar. So I think one thing I'm thinking about is, let me pull out one of my favorite diagram. The gentle slope system diagram. So the idea is basically the diagram that shows the program complexity and the difficulty of use. If we try to frame this as an end-user program tool, that means we start from here. We try to keep it easy to use, And then we try to gradually enable end users to do more complex things. Like for example, here would be just a simple replay, like record and replay macro. User just record something and we just replay exactly what it just did. That's very easy, but it's a very simple program. And then we try to gradually add new things, like we add parameters, we add concepts, we add conditionals. But the goal of what we're doing is we still want to keep it easy to use. And so far, at least from the usability studies we have run, we are fairly successful at that. Although one thing I want to say is, although some of the participants we run, they were non-programmers, they were still like mostly college students, so they are still fairly competent in terms of like general familiarity with technology. So for field deployment study, I actually plan to see if we can recruit people from more diverse background and see if they're actually able to do it. But coming back to the programming, the problem of programming tool, if we start from a professional development tool and try to make that easier to use, then we're basically starting from there. And so we start from like complex tasks, and then we gradually making that easier and easier. But at the end, I think no matter which direction we take, I think we're going to end up at pretty much the middle of this graph, where the end goal is to have a system like this that is capable of handling fairly complex things, but it still doesn't have any of those bounds, which means it doesn't have significant barriers to use. So I think that's the end goal, but I think we're still far away from there. But at this point, I think you raise a really good point. As we add in those more and more complex functionalities, one goal we have is to still keep it easy to use for people without programming skills.
I guess one other reason I bring it up is that another way you motivated this work was pointing back at some of the existing conversational assistants, Siri, Alexa, and all of these. There is this very real problem of users not knowing what they can do with these systems. They're not discoverable. But it seems like the more you kind of have to know what the system is capable of, the closer to those kinds of systems this end-user programming system will feel like, right? So I happen to be able to figure out that my phone can figure out the temperature, but as you pointed out, it can't figure out if I'm sweating. And there's probably a lot more subtle ground between those two where it might not even be as clear-cut to somebody who does understand more about how the phone works and things like that. I mean, is that one of the ways you want to be able to compare Sugilite to, say, a conversational assistant that requires less, like it's more discoverable what you can do?
Right. I think in terms of tasks, there are basically three categories of tasks. One is things that the agent know how to do. The second is things that the agent doesn't know how to do, but things that you can teach the agent. And third is basically things that are totally out of reach. I think for existing systems like Siri or Alexa, there's no category 2, right? It's basically 1 and 3. And as you said, the user doesn't really know the boundary of category 1. But I think in my system, I think the current state is the user still doesn't know the boundary of category 1. But the user kind of knows the boundary of category 2, which is things that you can do with existing mobile apps. So I think my approach is basically to enable users to, although they don't know exactly what the agent can do, but they know, okay, whatever I say, even if the agent doesn't know what to do, I can probably teach it because I know an app that can do it.
And then last question, it also actually goes back to something John talked about. So, big problem in the past with these systems is that even when they're fairly well developed and work reasonably well, people don't use them, right? So like I had CoScriptor installed for years, and worked at IBM for a while that summer, I never really found a reason to use it, right? One of the things that I thought you were going to do, which I actually thought could at least put a different spin on that usefulness problem, was going to be allowing me to kind of take my Sugilite scripts and take them off this phone device and onto something else, like an Alexa or like a speech assistant. This is actually what I was doing at IBM too, which for our purpose, we were repurposing CoScriptor for accessibility, because it kind of flips it around so that the utility trade-off is a little bit different.
Right.
And that might be true of speech assistants as
Right.
well. I just wondered, like, have you thought about, could you run your field deployment on a speech device instead of a phone?
Yeah, that's a great idea. We haven't tested, but it's actually something we discussed in the smart home paper, because we figured that as you said, one limitation of Sugilite, if you want to use it in a smart home context, is that because all the Sugilite scripts have to be executed on the foreground of the phone, which means that if you use it on your primary phone, and boom, there's a condition that triggers a script, the script will actually interrupt whatever you're doing. So one way we propose to solve this problem in the smart home paper is to have a dedicated phone to basically use for smart home applications, because Android phones are fairly cheap at this moment, so it's not a big problem. So yeah, that's something we can consider doing. Because I agree with you that if we are able to basically deploy this on, for example, smart speakers like Amazon Echo or Google Assistants, it's probably going to have different utility trade-offs compared with having this running on a user's primary phone.
There's a precedent. So Jeff Nichols, who some people know, Tesla, other people, they did this for CoScriptor as well. They make it run on the back end so that you could then speak to it. It does kind of change the. Should I maybe encourage you to look at that?
Sure. Okay, I'll ask a couple things. Actually, with that particular idea, Sugilite still requires you touch the screen and identify things on the app GUIs. So I'm not sure that would work. And also it assumes you're familiar with the apps, which if you are just kind of randomly using Alexa, it would be presumably pre-set up with random apps you may or may not be familiar with.
Right. But you can run existing scripts you created on the phone from Alexa.
Not only is this great work, but all of your subsystems have really super names. Thank you for that. Keep up the good work in naming. So my main question is putting all these pieces together. So for example, the script was designed with the original disambiguation mechanism in mind, the script view. Is that same view being used when you have Apponite style disambiguations where there's all these different tests that go into the figuring out what you're trying to click on, and is there a similar or is there going to be a representation for the conditionals? How is all this really going to fit together?
Yeah, the short answer to that question is no. Not all legacy parts are integrated into the latest version. But that's one of the major work that needs to be done before we have this field deployment study. Because we're deploying this in the field, so we really need all the components to be working together in an integrated way. So that's one of the main work to do is to deal with those engineering efforts required to have this one integrated system that we can feel comfortable deploying.
And you don't think that's It sounds like you don't think that's a serious research problem. It's just kind of fixing things.
Yeah, mostly, I think.
Is there anybody left who wants to ask a question? Okay. Do you guys want to go another round? Do you have more that you've saved up?
Yeah, I'll just ask, this is a good to lead into the future. So in the future work, that's a lot of future work you're proposing, right? And the timeline, in the ideal case, you do all of them. What would you prioritize in the future work? You have the better NLP, the error handling, the privacy preserved sharing, and the field study. If you had to prioritize, one or a small set of those, what would be the most important to you to make the system, more robust or usable or such?
Yes, so I think for research purpose, in terms of collecting more data, we're currently prioritizing privacy preserving sharing mechanism, because that would allow us to basically collect all the scripts the users are creating in all the later user studies, which I think would be valuable. But that's purely from like a research practical reason.
Okay. Well, you kind of already did that. So what's next after that?
Next after that, we're kind of doing the other two parts in parallel. So we're pushing forwards on both directions in parallel. So because both of those directions are, I'll say those are prerequisites before we can do a deployment study. Because if you have a crappy natural language understanding module, or you don't really have good ways of handling errors, I don't think we're going to have a successful field deployment.
All right, thanks.
So I guess to follow up on that, sorry, Tom, suppose, kind of getting back to what John said, suppose the field deployment fails in the sense that people actually don't use it for anything, or everything they try fails, or things like that. Is that like, okay, time to start over, or you need another 7 years to fix it, or, what is the fallback position?
Well, yeah. I mean, if the field deployment study fails, I hope it fails in an interesting way. Because if it fails because the system crashes a lot, that's not interesting. But if the study fails, people don't use the system because they have some interesting concerns or interesting rationales that can explain why they're not using them as often as we hope. I think those are actually valuable findings. So I think as long as the system doesn't really, fail because of it crashes or for those reasons, I don't think there's a way you can fail the field deployment study.
Okay. Tom, do you have anything else?
One question. To first order, it seems that in this work you're assuming the natural language understanding component is a fixed capability. It's given. It's not perfect, but we're hoping it's going to be good enough. And so my question is, to what degree is part of the problem learning semantics of new language, and to what degree, like for example, when you say order me cappuccino, it seems the initial semantics for the verb order is unknown, but now that I've trained the system, it would be reasonable to think that in some sense the system has the semantics for order. So in that kind of limited sense, you're already using the system to learn some new language in addition to learning the procedures to execute to achieve tasks. So my question is really, to what degree should we think of this as primarily learning procedures versus simultaneous learning of language semantics and procedures?
Yeah, that's a great question, because initially I was actually actively trying to avoid dealing with semantics because it's a hard problem. But I think now we really have to think about this problem is to what degree we want to actually deal with semantics. I mean, I don't think we want to go too deep into that problem for the sake of this thesis. Like, I'm not thinking. We tried a little bit. We tried like introducing external knowledge, like word knowledge, or like pre-trained language model into a system. I mean, that didn't really work out, but we also didn't really try super hard in those directions either. But come back to your question. I think the sweet spot we are targeting is to nerd the semantics, quote unquote semantics of those words in regard to the GUI and its structure and its contents. Because I think that's the interesting problem we're looking at is how can we basically understand those concepts using those resources without referring to, for example, pre-trained word embeddings or language models. So that's why we're also approaching the error handling problem by referring users back to the GUIs, because from those GUIs we can extract, for example, the structures of those GUIs and the contents already in those GUIs, and then we see if we're able to establish connections between what the user said to what we know are displayed in the GUI.
Okay. I'm good. That's a very open-ended question, but I think your answer is reasonable. So I'm good for now.
John or Jeff?
You're good.
Anything else? Okay. Well, thanks again.
There's one more question back there.
Oh, cool.
Yeah, I had a question, kind of related to John's point around who is this actually useful for? And you had mentioned that that one of the IT admins had brought kind of like an enterprise use case up. So I was wondering if you thought about testing it from like an enterprise context, because there's an analogy with RPA, the robotic process automation,
right.
And this seems like it could potentially be something that delivers robotic process automation type capabilities, but with like more of a gentle slope, like what you're talking about here, than current robotic process automation. So just wondering if you've thought about that.
Sure. That's a great question, because like the original CoScriptor system that was actually deployed in an enterprise setting, right? So in that paper, actually, it mentioned the sharing of those procedures actually carry two purposes. One is, as we mentioned here, basically automating repetitive tasks or to automating tasks that are not convenient to perform directly. But it also has a purpose of sharing how-to knowledge. So like, for example, if a company has a really complex reimbursement purpose, like a reimbursement portal that's difficult to navigate, I think the original CoScriptor system actually proposed a use case of using a task automation script to not only automating that task, but also for communicating how to do this task. So yeah, I agree with you. This is definitely something we can consider in the future work, is to see if we can find enterprise usage for our system.
I think, as I recall, the most popular CoScriptor script was one that changed your password 10 times on the IBM system, because you could only use the same password if it hadn't been used within like 10 times.
That's very clever. Okay.
Any more
Thanks.
questions?
All right. Well, we'll invite the students to leave, and we'll say bye.